Okay, I'm going to create a quick video to go through your study guide for the next unit on momentum. Since I'm absent today, we will cover this today, and then we're going to cover some momentum math today, as well as the district assessment. So we got a lot on our agenda today, so hopefully everybody's paying attention and ready to go. So I'm just going to cover the basics so we can get through this as quickly as possible. The unit is on momentum. Momentum is defined as the product of an object's mass times its velocity. So right here, mass and velocity. So it's pretty straightforward. An object that has a mass and is moving has a momentum. So if an object is not moving, it has no momentum. So given some examples of objects that have momentum, there's two ways for an object to have a large amount of momentum. And that would be for if the object is moving very, very fast, like this example of this bullet right here, moving really, really fast. So this bullet would have quite a bit of momentum because it's moving really fast. Or this train is a very, very massive object, so it's going to have a very large mass, and so therefore even if the train's not moving very fast, it's still going to have a large amount of momentum. And objects with a large amount of momentum are very hard to stop, and we'll talk about what that means a little bit more. Here's another example, but these football players would have a relatively small amount of momentum when you compare them to the bullet or this train, because they're relatively not that large, and they're not really moving all that fast. So they have a relatively small amount of momentum. And then here is finally an example in this mountain here of an object that is obviously huge and massive, but has no momentum because it's not moving. So objects need to be moving and they need to have a mass. So there's the key takeaway there for momentum. Alright, moving on. So number 4 here is how is it calculated? Again, it's calculated by taking the mass times an object's velocity. The formula for it, the symbol for momentum is going to be P. And it's not M because M is already used for mass. So it's going to be P. And its formula is going to be mass times velocity. And the unit for mass, as you are aware, is kilograms, and the unit for velocity is meters per second. So momentum is just going to be kilograms times meters per second. It doesn't really have a fancy name or anything, so it's just kilograms times meters per second. Now, momentum is a vector, and the reason it's a vector is because momentum, like all vectors, has magnitude and it has direction. And the reason it has direction is because velocity has direction. Velocity can be positive or negative, as you're aware, and so therefore that's going to give you either a positive or a negative momentum. So anytime a vector is used in a calculation, then that's going to make that particular variable also a vector, because again, the vector velocity could be a positive or a negative number. If you multiply that times this object's mass, you're going to get a positive or a negative p, which is the momentum. So moving along. Here's an example problem of how to calculate momentum. It says, what is the momentum of a golf ball that has a mass of 0.046 kilograms and a velocity of 10 meters per second? So pretty straightforward stuff. You put the 4 steps. You got kilograms. You got velocity. You got the formula, which is P equals mass times velocity. And so then you just take the mass times the velocity. And it's going to give you the P value, in this case, of 0.64. And again, the unit in that is just kilograms times meters per second. So that means that all the masses have to be in kilograms and all the velocities have to be in meters per second. Alright, moving on to the next one. Now let's talk about impulse. So the impulse is what is felt that causes an object to change its momentum. So it is the thing that causes objects to change momentum. So like I said, when an object is really, really big and moving really, really fast, it takes a lot to cause it to slow down or to speed up. So changing in its momentum is done primarily. You can't change an object's mass. So to change an object's momentum, what you're really changing is its velocity. The only way you could change its mass is if you just like took a hammer or a hacksaw or something, and you just chopped off part of it. And so for realistic purposes, since we're not going to be chopping things up here in physics, we change an object's momentum by changing its mass. And we do that, or excuse me, by changing its velocity, not changing its mass. Mass is constant. So we're going to change an object's velocity by applying a force to that object. So even though impulse is defined as a change in an object's momentum, that momentum is changed by applying a force. So here's the definition. Impulse is the product of a force and a time interval. So it's force times time. So it's the force times the time that force is applied to an object. So if you apply a force to an object, it's going to change its momentum. So here are two examples. Here, this guy is going to apply a relatively small amount of force, but he's going to apply it over a long period of time to this guy's face, and it will give you a change of momentum. The same change of momentum can be obtained by applying a large force over a very quick amount of time. And you notice here that this guy, they're saying crunch. So this is a much harder, more impactful, more damage is done to the guy's face because the force is large and the time is small. Well, here, if the force is small and the time is large, he's still smiling and it's a little poof, so it's not nearly as much damage done. So if you want to reduce the damage done, you're going to apply a force, a small amount of force over a long period of time, which will cause an object's momentum to change. Because remember, impulse is going to cause an object's momentum to change. So that's what this is. How is impulse calculated? It's calculated by the change in momentum. And the formula for doing that, the causing an object to change momentum, is you're going to take a force and apply it over a period of time. So the greater the amount of time for which a collision, in this case the collision between the guy's face and the fist, the smaller the force that has to act upon it to end up with the same amount of momentum, or the same amount of impulse, which is change in momentum. So for example here, I'll just put some numbers to this. Let's say I want an impulse of 10. Well, if I apply a force of 2 for a period of 5 seconds, I can get 10. Or I can apply a force of 5 for a period of 2 seconds and I can get 10. Or, even worse, I can apply a force of 10 for a period of 1 second and get 10. Or it can get worse and worse and worse, right? So my point is that you can apply a larger force for a smaller time, or a smaller force for a larger time. The greater the force, the greater the damage. The force of a collision is what causes the damage, not the period of time for which that force is applied. So you're going to want to, in terms of having collisions and accidents, you're going to want to have the force applied over a longer period of time to reduce the amount of damage, like in car accidents and stuff like that. That's the job of the seatbelt and the airbags, is to reduce the force, apply that force over a longer period of time, slow you down slower. So it slows you down slower, changes your momentum slower. Okay, so here we go. So it says, thus, to minimize the effect of the force on an object involved in a collision, the time unit must be increased. So if you want to reduce the force, you increase the time. If you want to maximize the force, then you reduce the time. If you want to maximize the force, you reduce the time. Moving right along. Alright, so now we're going to talk about the law of conservation of momentum. So basically, the law of conservation of momentum, it says that when there is no external force involved, if there's no external force involved in a collision, just like you've got going on here with these Newton's balls, there's no external force going on with this collision. This Newton's cradle here is showing you that all the momentum is transferred from one end all the way through the two in the middle to the other end. So what this means is that the total momentum in a system that is closed off to the rest of the world is conserved. Another way of saying that is the total momentum of two objects before a collision has to equal the total momentum of those same two objects after that collision. So we can do some interesting math with that, and we're going to talk about that a little bit more later on. But basically what we got going on here is before the collision, you could calculate the total momentum of these two objects, which would be the the baseball player here and the baseball by multiplying their mass times their velocity. And this guy's not got any momentum because he's standing still, so his velocity is 0. So the total momentum here is going to be the 45 meters per second times the 0.15 of the ball. And now here on the other side of the coin, we can calculate that if this guy still doesn't move, then we can determine that the ball would have to be continuing to move. So even though it doesn't always look like it, this guy will move some amount of distance because that ball is going to slow down. So when its velocity changes, so would his have to change. It will transfer the velocity of the ball to him, but not as much of it because his mass is bigger. And we'll talk about that a little bit more as we move along. But essentially, that's what we're going to do here. So here we would take 3,000 times 10. That would give me 30,000 here. And on this side, it's 3,000 times 0, so that's 0. So the total momentum before the collision is 30,000. It has to equal the total momentum after the collision. So this momentum total would have to be 30,000 too. So if this car is going, if it's got a mass of 1,000 and a velocity of 10, so this car's momentum is 15,000. Then we would know that this car's momentum has to be 15,000 as well, because these two together have to equal the 30,000 that was there before the collision. Since its mass is 3,000, then we would know that its new velocity after the collision would be 5 meters per second. So we can use this whole conservation of momentum to solve for velocities of objects before and after a collision, because the 30,000 of the total momentum of both objects before the collision must be equal to the 30,000 of the total momentum of both objects after the collision. And with that, we are just about finished. We've got one more slide left, and that is basically just giving us the formulas for what we just described here, which is this law of conservation of momentum. The total momentum, this is P, that's for momentum, before a collision has to equal the total momentum after the collision. So that means here's our two objects. This is object 1. So this is object 1 and object 2. If we add their two momentums together, which remember you get momentum by taking mass times velocity. So this is the momentum of object 1. And this would give you the momentum of object 2. So if we add those together, this I means the initial momentum before the collision. They have to equal the momentum of both of those same objects after the collision. That's what the law of conservation of momentum says, is that these two added together before the collision must equal these two after the collision. So we can say if you take the mass times velocity of one object plus the mass times velocity of the other object before the collision, they got to equal the mass times velocity of those same two objects after the collision. What can happen is that this one can have a lot of velocity, this one can have none, and then it can transfer, and then all of a sudden this one's got velocity and this one's got none. So it can transfer some or all of its velocity to the other object, since obviously we can't change its mass. And that kind of transfer of velocity is what we call an elastic collision. Elastic collisions occur between objects that are rubber or that will bounce. And so objects that bounce will basically transfer their transfer their velocity from one object to another. Now, an inelastic collision, that's a collision where the objects would stick to each other. So we notice what happens here. We have the same way to calculate before the collision occurs. So this is before, they're all just moving along. Here's object 1, it's mass times velocity, it's cruising along. Object 2, mass times velocity. Then they collide and they stick together. So the masses of the two objects now become one. So they stick together. So this is the two objects stuck together. Two objects stuck together. Stuck, S-T, stuck together. And so then all of a sudden they're traveling together with only one velocity. Here they were traveling apart so they could have two different velocities, but then when they collide with each other they stick together like glue, and so their masses are combined and you have one velocity. But still, if I take the total on this side and the total on this side, it has to equal the same thing, because again, the law of conservation of momentum, no matter which kind of collision you have to, this side of the equal sign has to equal this side of the equal sign. And we're going to be able to do things with these formulas that will allow us to solve for what happens to this change in velocity as a result of this type of collision, and what happens to the change in velocity after the result of this type of collision. Really, that's what we're all after here, is the change in velocity. Alright, so if there are no more questions with this, that should take care of your notes for this unit, and next I will have a video for your math, and the substitute should show that next.